Hi everyone and welcome back to another 247 CTF YouTube video. The format of this video is going to be a bit different than the videos that are usually uploaded to this channel. Usually the videos are completely scripted. I read the script from start to finish, then I do some editing, create some video, chop everything up and glue it all together. I haven't found the time to do that recently, so rather than not upload anything, I've decided to do a live recording. And the videos on the channel are usually in sort of two separate groups. So we have the game hacking videos and we also have the capture the flag videos. So we have the CTF write-ups and we have sort of the intro to CTF videos. And so I'm going to try and combine both of those things, and we're going to do a live reversing session. And what we're going to focus on is we're going to try to find an old Age of Empires trainer, and we're going to reverse that trainer and see how it was implemented back in the 1990s. So let's get started. Let's open up Chrome in an incognito browser and search Age of Empires, Rise of Rome trainer and see what we can find. So let's just open up the first three links here. So we can see here on IGN, it's listing all the different cheat codes that you can use in the game. So we've previously talked about this and shown how to reverse engineer the game and figure out the encoding, how these cheat codes were being encoded within the binary. But this is not really what we're looking for. Yeah, Games Radar looks very similar. It's just got the cheat codes in here, which again is not that useful. It's not what we're looking for. Okay, so here on Game Burn World, we've got a couple of options. There's 4 different trainers here. So let's just pick I guess this is the most recent one. Let's download it. And it's password protected, so let's extract the archive. GBW. Another archive. And here we have the trainer, RORTRN. And we can see here that it's from 1998, so quite an old binary. Let's take a look in CFF Explorer, and we can see that it's a 32-bit binary. It was likely compiled with Microsoft Visual C++ back in 1998. And in CFF Explorer, we can jump down here into the import directory. And from here, we can see the different modules, the different DLLs that are being referenced by the application. And we can also see the functions that are being called as well. So this gives me sort of some high level idea about the kind of functions that are being called and the kind of things that the binary is potentially doing. Because just because this is an old binary, we don't necessarily know that that doesn't mean that it's not going to be up to no good if we choose to run it in the VM here. I'm looking to see if it does anything like read process memory or write process memory, because those are the kind of function calls that I would expect based on how we implemented the cheats in previous videos anyway, but I don't see anything here that makes me think that. So let's just quickly have a look in PEID as well. So again, we can just drag and drop here. And we can see similar information here. So this is a good way to get a high level overview of the kind of file that you've downloaded and how it's been compiled as well. But let's jump into Ghidra. Not that Ghidra. And start doing a little bit of reverse engineering. So we can start a new project. Trainer demo live. Can drag and drop the binary into Ghidra. We can see the similar x86 PE information that we already saw. And we can see that Ghidra's extracted some more information about the binary, and it's also calculated the MD5 and the SHA-256 hash. So these hashes can be really useful if you download something and you're not sure what it is. So for instance, if you're doing reversing malware, these hashes can be really useful just to Google and see if anybody's already analyzed it before, if anyone's already done a write-up on it, or whether or not it's been uploaded to any other sites where you can leverage that existing analysis. So while Ghidra is analyzing this binary, we might do just that. So let's kick off that analysis and let's have a quick... I didn't copy that hash properly, apparently. So this is what happens when you do it live, I guess. Okay, we have to wait. Let's kill that. Not sure how to get that hash again. No, that wasn't the way to do it. Generate checksum. Is that what we want? Let's try this. There we go. Okay. Try again. Okay, so after all that, nothing really interesting. Let's just check on Virustotal, because sometimes hashes don't show up in the Google results. Here we go. So we can see we got one hit on Virustotal from 3 months ago, so quite recent. We can see that one of the AVs thinks that it's a DDoS tool, HackNuke 19, and nobody else seems particularly bothered with it. And what is it getting triggered for? So it writes a file, access a registry key, and it kills Windows Media Player. That's interesting. Okay, but Ghidra's flashing away, so we can see that the analysis is done. Okay, so this error is just because I clicked Analyze All when I was loading the binary, and we can see that Ghidra's complaining because it can't find this PDB file. I forget exactly what that stands for, but it's basically a database of all the debug symbols. Yeah. Proprietary file format for storing debugging information about a program. So if you have that debugging information and you load that into Ghidra as well, that can make your reverse engineering job a lot easier because you can reference that debug information from Ghidra. So the analysis is complete. We can see these same import tables that we saw with CFF Explorer. And we can also see the different sections of the binary. So we care about the text section because that's where the executable instructions live. And specifically, we can start here at the program entry point. So if you're not sure where to start, this can be a good place to start. It depends a bit on the size of the binary and what you're trying to achieve. But we can see a bunch of functions here about the application getting started. We can also see a bunch of these Windows API calls. And if you're not sure what these do, then MSDN has a good definition. So MSDN get module handle A. And here we can see the MSDN definition of this function retrieves a module handle for the specified module. Okay, so I mean, you can click around sort of arbitrarily from the entry point, but usually what I try to do is look for interesting functions. So before some of those interesting functions, so write process memory was there, I just didn't see it. No read process memory though. So clicking around it is hard. You can look for the functions that you think are interesting, and then another place that you can look is to look at these defined strings. So to look at the strings that are being used by the application, and that might also give you some idea of an interesting area to look. Okay, so we can see, yeah, Age of Empires is being referenced. We can see 900,000 food, gold, stone. I suspect wood will be somewhere too, yeah, and wood as well. We can see, yeah, that there's some text here, run the game before, so it's probably checking that the game process is running before it does anything. And yeah, we can see references again to this write process memory function. So let's go straight there because this is looking quite interesting for understanding how this hack works. And what we can do in Ghidra is you can right click on this function call here. We can go to references and we can show references to this address. So we can see different places within the code that call this function. And we can click on these now. We can look at the decompilation. And I can already see that this is an interesting function call. So we can see that this function call is calling find window A. And again, let's just look this up in MSDN. Retrieves a handle to the top level window whose class name and window name match the specified strings. And those strings are Age of Empires expansion. So it's trying to get a handle to the window called Age of Empires expansion, which is probably what the game is called, or at least it was what it was called when this trainer was written, so that then the trainer can get an access to that handle. Then it calls get window thread process ID. It opens a handle to the process. So if the process returns, if this call returns 0, so we can check MSDN open process. So we can look at the return value here. So this is the function call, these are the parameters it expects, and this is the return value when it returns. It says if the function succeeds, the return value is an open handle to the specified process. If the function fails, the return value is null. So we can see here, if the return value is null, then it's failed. And then we get this error that says run the game before. So if it hasn't failed, we continue. It makes a annoying noise for some reason. Then it calls the write process memory function. And I've lost that now. I didn't look it up yet. So write process memory writes data to an area of memory in a specified process. The entire area to be written to must be accessible or the operation fails. So we can see the parameters the function expects. It wants a handle to the process. It wants the base address, which is where data will be written to. It wants the data to be written, which is passed in as an LPC void buffer. End size, which is the amount of data to write, and then a pointer to the variable that receives the number of bytes transferred as part of the process. So if we look back at the function, we can see each of those things. We can see the process it wants to write to, the address it wants to write to, what it wants to write, the size of the write, and yeah, the variable that says how much was written. After the write, PC bar 1, which is a char pointer, gets assigned to this, which is 900,000 wood, which we saw before. And then this function is called with that string as a parameter. And this function is calling message box A. So when this function gets called, it will pop up an alert and give some message to the user. So that message in this case will be 900,000 wood. Okay, so that makes sense. Basically, something happens, so there's probably some button or some hotkey you have to press. Then the trainer will get a handle to the process. It will check that that handle is valid. Then it will write something to some address, and then it will alert the user that has occurred. Oh, and if it hasn't, then it will give the error to the user, so tell the user to run the game. So if we look at the other references to write process memory, okay, we can see it's basically doing the same thing. So this is for wood. This call is for food, so you can see the string here has changed. And also these addresses have changed, so the write address and what's being written has changed. And they're going in increments of 4 bytes. So this is again congruent with what we've seen when we've been reversing as part of the game hacking videos, which is that in memory, the game is storing the player's wood, food, gold, and stone, one after the other, each stored as a float. I'm not sure why it's stored as a float, but it is. So there's the wood, food, gold, and stone next to each other. What this binary is doing, what this trainer is doing, is an external hack, getting a handle to the process. Then it's writing some value to that address. And what is it writing to that address? 00BA. These are different, right? So they're all writing the same value, which is this 00BA5B49 address, but this is probably a float value. So we can verify that. I don't have Python installed here, but what we can do is we can just run the game and we can test it out. Okay. So before we run the game, if we open the binary, what we should see is that we get an error, right? Saying that the game's not running, that it can't find the game. Okay, so we don't see that. Good start. Or is that only, oh no, so that's only after we press the buttons. So when it's getting to this piece of the code here, it can't get a valid handle because it can't find the game process based on the name, and it's telling us to run the game. So let's do that. Just using DXWin because then we can run it in Windows mode and it won't take up the whole screen. So we've got the game started here. Start the game. And now when we press the buttons, it shouldn't give us the error anymore. So we press wood. It says 900,000 wood, food, gold, stone. So the trainer's not complaining anymore. Jump back over into the game. But we don't have extra resources. So something's gone wrong here. Let's use x32 debug. Let's attach to the game. And let's first show what it's trying to write. So let's just get an idea of that. So I think an easy way to do that's going to be just to edit this random memory section. Well, let's first view it as a float. And then let's edit it. Not like this. Modify value. So let's put these bytes in here that are getting written. So 00. Can't do that. Okay, I'll enter them as the expression. And we have to remember to reverse the byte order. So we go 4, 9, 5B, BA. 00 00BA 5B49. Okay. And we can see that that hex value, when it's expressed as a float, is 900,000. So the string was accurate with what it was trying to do. It was trying to write 900,000 to that address, so that seems okay. The process is called Age of Empires expansion, so this also seems okay. So that means that probably where it's writing this address is wrong. So this is a hard-coded address. So we talked again in previous videos about getting dynamic pointers to find this address. In here, the address has been hard-coded. And so what that basically means is that if the version of the game that we're running here is in any way different to this version, well, if the location of the data structures is in any way different, then this is not going to work. Because instead of writing 900,000 to our food location, it's just going to write it to some random address. So we can look at where it's trying to write in the debugger. So we can see the address of the binary here at 004000000. And this is a predictable address because this old binary doesn't have any ASLR. So every time we run it, we know it's going to be always starting at this address every time. We can see though that this 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Yeah, so we can see that this is trying to write beyond the scope of where this binary is sitting in memory. So whenever this binary, this trainer was created, the Age of Empires game must have been significantly larger. So what's probably happening is it's trying to write somewhere, and that write is failing because it can't write to that address. So we can check that assumption. If we instead attach to the trainer instead of the game, and we'll need to restart the game because we just killed it. And we know where this write occurs at this address here, so we can Control C. We can jump to this address with Control G. And we can set a breakpoint with F2. And here we can see this write process memory call in the debugger. And this is for adding 900,000 gold. So now if we click the gold button, we should hit that breakpoint in the debugger, and we have. And down here we can see the call on the stack. So here we can see this is representing H process. This is representing where it wants to write. This is that buffer. This is the size, so 4, and then this is where it's going to store the total bytes that have been written. So we can step over this by pressing F8, and that will go ahead and make this call. And what we should see, or we'll probably see, is that the return value is stored here in the EAX register. So the function's return value, and it's returned 0. So if we go back to MSDN, if the function succeeds, the return value is non-zero. If the function fails, the return value is 0. So this function call has failed. And that makes sense with what we saw, right? Because the location it was trying to write to doesn't exist, or the memory map didn't exist for it to write there. So when it tries to write to that address, it can't write there, so it fails. Yeah, there's no error checking here around whether the write process memory call was successful. And so it's sort of failing silently. So it thinks it's writing the gold to that address, or the wood, or the stone, or the food, but it's actually failing. So this is a bit disappointing. We could fix this. We could change this address where it's writing to by using dynamic pointers, which we've done in a previous video, but I think that would be a bit overkill for this video. So I think we'll wrap up there. We reversed the trainer. We figured out how it works. It's quite similar to one of the early iterations of the trainer that we made for the YouTube channel. Let me know if you like this format, or if you want to see more videos, these live videos like this, which include mistakes and me needing to Google things and not knowing stuff. I can guarantee you in the other form of the videos, I do this all the time as well. The upside to these videos is that I can pump them out a lot faster, a lot more consistently. The quality's a bit more off the cuff, so a bit less polished, I would say. But I think that this could be a good way to make videos moving forward. Maybe we can have some live videos and still some more of the other structure, just depending on time commitments and what works. But that's it for now. So thanks, and see everyone next time.